Hi guys, I'm Ben, and today I'm going to discuss my codes on machine problem 3, solving ordinary differential equations set A. So this problem has two parts. The part 1 deals with the creation of a code that will implement Euler's method uh, for any function of the form dy dt. It's equal to f of y in t, where y, this should be y, is the independent variable and t is the dependent variable. So this code should have a format of t sol y sol is equal to Euler method dy dt t I t f h and y naught, where dy dt is the function on the right hand side of the differential equation. Ti and tf are the initial and final values of the desired range of the independent variable. H is the step size that is required, and y naught is the initial value of the dependent variable y. So the output variables are tsol, which is the vector over the range of independent variable using the increment h, and ysol is the vector of solution for dependent variables. So for part 1, uh, here's the code that I made. So it has the form tsol ysol with method dt ti tf h y naught, and next is the definition of tsol, which is the vector over the range from ti to tf with increments of the step size h. And ysol is the vector of solution, and I add another condition, which is uh, ysol quantity 1 would be equal to y naught. There's a reason for that, and because and loop, a for loop here, because first method is a numerical approximation in solving ordinary differential equation. So there's going to be a lot of iteration, and we're going to use this condition. So to give you an example, here's what Euler's method. Um, Here's an example of Euler's. So in y1, we're going to use y naught plus the function at y0, y naught, and times 0, which is equal to this, times the step size, and for y2 going to use y1, for y3 going to use y2. See, so it's always I minus 1, like in this code, and that's code for the part 1. So for the part 2 is the application part. We're going to use different MATLAB scripts to solve the differential equation dy dt is equal to y times t cubed minus 3 halves times y over the interval t is equal to 0 to 2, where y naught, our initial condition, is equal to 1, using the following. So first, we're going to use symbolic math. Second, we're going to use our code to solve for the Euler method with step size 0.5 and 0.25. And lastly, we're going to use the ODE 45 built-in function in MATLAB. So, everything in one script, display all the results on the same graph, on a separate graph, like a 2% relative error. So for every step size, we're going to find the percent relative error, which is just the uh, exact values minus the approximate values over the exact values times 100%. And for the application, as always, we start by clear all, close all, CLC, and these are the given for the analytical solution. Uh, and these are the given for the ODE. So for the analytical solution, we're going to use symbolic math. So sims y of t, and the equation is the diff of y and t is equal, so this is the dy dt is equal to y times t cubed minus 3 halves times y. And the condition, the initial condition is that y naught is equal to 1. So solving the initial condition, we have ya for solving y analytically, and t solve with equation and condition. So letter B, in Taylor's method, we're going to use our function. So pH1 will be the t solve. H1 means with the step size, which is step size 1, which is 0.5, and by H1 for y solve, Euler method, dy dt, that's our function. This is an knowledge function. Pi, which is 0, Ef, which is 2, and H1, which is 0.5, and the initial condition, which is 1. So after that, I solve the first percent error, so E1. Here you can see the formula for percent error. I did the same for the second step size, which is 0.25. And for the last solution, ODE 45 is what is the function, the range, and the initial condition. And I also use the same percent relative error formula to get the percent error for ODE 45. The next part is plotting the numerical values. So this is our first figure, and problem says that this should have 4 graphs. So the first graph is the plot of the analytical solution. The second is the Euler method for step size 0.5. And the third is the plot for